All right, welcome to data structures. So at the end of this lesson, you should be able to describe how data structures are used and implement a stack. So let's talk about this first one, describing how they are used. I'm going to start by giving you a list of super common data structures you've probably seen before. Might give you an idea. So one of the most basic ones is called a list. There's a particular variant on it called an array. We know that one. Stack, queue, hash, linked list, tree, and graph. If these are the only data structures you ever learn, you'll probably know more data structures than most programmers. Each one of these has some kind of data storage on it and some operations that we can run on it. For example, one more that's probably worth knowing is a set. So for example, a list is any collection of things. Call that a list. If it's important, like the order that they occur in, then it becomes an array. And what are some operations that we take on an array, for example? What was it? Okay, so if the order is important, it's an array. That's the primary difference between a list and an array, is the order is important in an array. So give me some operations that we can take on an array. Map? Not map. That's not a part of arrays. That's a part of enumerables, which are a kind of data structure as well. Good guess, though.
We can find something by the index.
Okay, we can find something by index. That's an operation we can take on an array. What else?
Add or take away things.
Ooh, but we have special words for them.
Push.
Push and pop. And anybody remember what the ones on the other side of the array are? Shift and unshift. So we can access something by index. We can push, we can pop, we can shift, we can unshift. That's the definition of an array. In languages that support such a thing, like JavaScript and Ruby, we can map, we can reduce, we can filter. Those are not parts of an array, though. We're talking something way more abstract than how it's implemented in any particular programming language. But definition of an array is that we can perform those operations on it. Part of data structures is also knowing what the operations are called and what the pieces in it are called. For example, a part of an array, everybody know the technical definition for that? It's an item. That's close, though. What was it? Element. Element. That's what it is. Arrays have elements. And we can take those operations on them, push, pop, shift, unshift. We can also get the length of the array. It tells us how many things are in there. All of those are part of what it means to be an array. An important distinction, too, is that with push, pop, shift, and unshift, that means we can do operations on either side of the array. We can't with a stack. Stack works very similar. We also have push and pop with a stack, but we don't have shift and unshift. All we have access to is one side of it.
So, that's still two-dimensional data storage?
Mm-hmm. Still two-dimensional.
One is vertically, one is horizontal.
Well, if we're going to visualize them, we might say something like a list It's really just kind of a collection of stuff. They don't necessarily have an order to it.
And they have to have the same data type across the board with the list.
Not in a list. They technically do in an array. In an array, every element is supposed to be the same data type. There's a name for ones where they're mixed data types. It's another data structure. It's more common in Java and C# and Swift, called a tuple. Tuple is like an array except the data types are mixed. So in an array,
Tuple, like you can even make any game change for the tuple, like you can fix that.
yes. So in an array, these have little addresses. It's now. This is a really fun reveal. I'm curious how you guys are going to take this. You ever wonder why the first one's called 0? Let's say I have 2 of these. Okay, so I'm storing these in the computer. And these arrays each have an address, like on the physical hardware in memory. So maybe we say this one is address 2513 or something. And we go 14, 15, 16, 17, 18. All right, this array is at 2519. So in my programs, when I'm accessing this array, when I grab that thing in memory, I go, okay, well, that array is stored here. And so I jump over to that array. Does anybody see the pattern with the elements on that?
Oh, makes the first one 13 basically, right?
They're offsets. How offset is this element from where I know the array is being stored? I keep track of this. I don't address this separately. I say it's in this array, offset by this many. That's why arrays are 0-based. Because down at some level, each of these things needs to get stored in a physical thing. That's what this computer science shit's all about. It doesn't have anything to do with application development. It has to do with theories of computation and storage and all that kind of stuff. We wouldn't even necessarily be talking about silicon-based electronics. This stuff we can do with pieces of wood and dowels and stuff. Doesn't matter. We're at that level of abstraction. But that's why. That's an array. That's a list. And with arrays, we can take stuff in, pull stuff out from either end, and those each have names. Versus, say, a stack, where I have these things. I can only add stuff to the top or pull stuff off at the top. If I want to access this element, I need to take off the one above it. Otherwise, that's all I can see. So let's circle back to our objective, which was describe how data structures are used. Wow, that seems pretty stupid. Why would we want something that's less useful than an array? Or if we look at its close cousin, Q. Q's have items in them or elements. And with these, I can take stuff out there and I can put stuff in here, but that's it. That's all I can do. Why? Why don't I want just one that does everything for me? The possible reason to do for that. Jesse. I like that. If we're modeling a problem where it wouldn't make any sense to put something into the bottom or pull something out of the bottom, we reduce potential error. Then what else?
Well, I think that's really good concern to performance, so with the rest.
And that's I'd say Jesse's answer is about 20%. That's about 80% performance. Because if the thing that I'm working on can only do these things, and to Jesse's point, it only needs to do those things, I can make assumptions about that data that I can't otherwise. And how I can operate it, and how I can write little algorithms down at the processor and motherboard and bus level to address that without having to handle 101 corner cases on it. Because it's got a reduced set of operations. For example, a linked list. There's a few different kinds of linked lists. They're very, very similar to arrays in that they have an order to them, but they're also like lists. So with a linked list, I've got this big collection of crap, except these do have an order to them. What they do is they link to each other. You go, this is the next one. This is the next one. Then this one. Then this one. So the advantage there is with arrays, these all need to be every single element needs to be next to each other on whatever the storage device is. So especially if you imagine a scenario where we're taking stuff out and putting stuff in all the time, and these are changing size, then we constantly need to rearrange where these things are. Because if this has 150 elements in it, it needs somewhere in memory where we have 150 adjacent spots. And then when it becomes 151, maybe it doesn't fit there anymore. Now we got to move it somewhere else. Ugh, gross. No such problem with a linked list. Linked list, these can be all over whatever the storage device is, and they just point to whatever the next one is. There's no big thing that knows where everything is, but we can traverse a linked list by just going next, 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 next. And how do we know we're at the end? When it doesn't link to something else, you're at the end of the list. Ta-da! Oh yeah, that's the whole thing. You're getting the advantage of a list in that you can put them all over whatever your hard disk is, but they don't have to be right next to each other.
How is that a performance enhancer?
Sure. So if these things are all right next to each other, and I'm taking things in and pulling things out, that's changing the size, which means potentially every single operation, I have to move the entire thing somewhere else. Now what I lose on that though is I can't randomly access stuff anymore. If I want to get this item right here, I need to start at the beginning and keep asking next until I get to it. These things, I can randomly access this as quickly as I can anything else. And so since that lookup time is constant, doesn't matter how big this array is, if I'm accessing it by index, it takes the exact same amount of time every single time. Versus this, where every time this list gets longer, on average, I'm going to have to look a little bit longer to find a particular thing. And so we say that this is an order of n. As this gets bigger, it gets proportionally longer to find something. Where in an array, no matter how big this gets, it takes the exact same amount of time to find something. So the reason that people ask you this kind of shit in interviews and why this isn't cracking the coding interview and why computer science degrees are based around this is that somebody needs to figure this shit out. It's how computers work. It's why our computers get faster and faster every year. It doesn't really have anything to do with application development. To wit, what is our, we have one data structure really in JavaScript. What is it? Object. Arrays, they're actually objects. Sets, they're actually objects. It's just a bunch of smoke and mirrors. Even things that like, if you were to implement a stack or a queue or whatever, it's just smoke and mirrors around fucking objects. JavaScript compiles down to C++. C++ does a lot more of this kind of stuff. And even below that, once we're getting into like our assembly language and that kind of stuff, that's where they're dealing with a lot of these problems. They're not hyper relevant to a lot of application development. Which isn't to say they're useless, especially stacks and queues and graphs and trees and some of those kinds of things. There are a lot of problems that are really elegantly modeled by these things. For example, I once worked on an app that was like keeping track of train timetables or something like that. All right, well there's 24 stops or whatever it makes during the day, and I just want to know what the next one is. Queue, really elegant data structure for that. So I make something that kind of looks like a queue, and I can dequeue whatever the most recent thing is. That's my next train stop. And then I enqueue it back in the beginning. And so then it keeps working through each of the upcoming stops, and then that one comes up again. It's handy to know, but it's not why you're being asked these questions in interviews. It's because this is what they do in computer science degrees, and they want to see if you were paying attention in class. And they think that's the only way that people come into this field.
Do arrays have limits on how many elements they can have in certain languages?
I mean, you're limited by the hardware at some point. There's only so many spots. And really, arrays are not supposed to be, well, I guess this isn't all the way true. I was gonna say you're not supposed to be able to like dynamically size them. You declare how big they are up front, and really every time you like push or pop into it, you're technically making a new array. I don't know, above my pay grade.
We got a question asked in the interview, like asked how can you reverse or replace?
Yeah, that's a good one. All right, so I have a linked list that looks like this. I want everybody to think to themselves for a sec. If I had to reverse this list, meaning all of the arrows just start pointing the other way. I want you to think logically through your head how you would make something like that happen. I'll give you a second. Anybody get one? How can I reverse that linked list? Just make the arrows point the other direction. Yeah.
You go through it and you check if it has a pointer to the next one. Then you, like whichever one doesn't have a pointer to the next one is the end. And you start a new linked list from that one. And then you keep running over and over.
That's it. So I need to be able to kind of see, I need to be able to like keep this window of two, basically, where Or yeah, I guess you would probably better just keep going. So we say, all right, we get to the end. This is the start. This is the origin block of the next linked list. All right, what has me as their next? Well, it's this one. Cool. That's my pointer. I'm going to move that one over here and make a pointer to it. All right, what had that as its next? Well, it's this. And you keep going until you're at the end.
You're making a copy?
Yeah.
Okay.
And then like some jackass might say, all right, well, how would you do it in place? And then these are just, they're like brain teasers.
In what?
So in place would be without making a new linked list. All we get to do is move the pointers, but we can't make a new copy. And so you'll get like stupid brain teasery kinds of questions like that, but there's no fundamental truth about the universe that you have to know. They're just like Sudoku puzzles or something like that.
Can you answer that by just saying get better hardware?
Get better hardware so you don't have to do it anymore. Find a package that does this because nobody has reversed a linked list by hand in fucking 75 years.
The linked list, does each item have?
No, that's the thing about it. You can't randomly access any element you want. You have to go through the entire thing to find something. Hmm? Yeah.
So, for each areas in the list, so can that person with the first node be an array, and the next one be an object, and the next one be a string, or the next one?
Yeah, no restrictions on what each part of a linked list can be. So arrays, they all kind of have to be the same thing. And part of that is that for this indexing scheme to work, all of them have to be exactly the same size. So it makes sense that they have to be the same data type. Because at some level, we're not even talking about string anymore. We're talking about strings of 255 characters. Like it's a fixed amount of memory for each one. Since we got through most of them already. List, array, stack, queue, linked list, tree, graph, and set. Set's super easy. Sets are lists where everything is unique. And so as you're adding something to the list, you see if it's already there. And if it's already there, you don't add it. And if it isn't already there, then you add it. So it takes a little bit more time to add things, but you can imagine scenarios, some of you used these in your projects recently, where you don't have to filter out duplicates or something like that. A set can't have duplicates. So it becomes a lot easier to retrieve a unique value, even if it's a little bit slower to add. And every single one of these data structures has a trade-off like that. Whether it's slower or faster to search, to like look something up, whether it's slower or faster to go through every element in something, slower or faster to add, to remove, to modify. That's why all of these different ones exist, is they have different, to sort it, these sort very differently. So what are you using it for? And that's like the most aggressive question you'll probably get in computer science-y kind of stuff is like, given this problem, what data structure would be most appropriate? And so that's really just a matter of either being able to reason out or just memorizing what the big O notation is for various operations and shit. A lot of this stuff you can kind of figure out though. If you know that linked lists, they don't have knowledge of the total list, they just have these pointers. Okay, so any kind of like sorting operation on that is going to be slower because we have to go through the entire list to find anything. Whereas something like sorting a set doesn't have duplicates, so it's probably going to be quicker to sort, that kind of stuff. Okay, cool. So, hash. If you haven't picked up on this yet, a hash in Ruby is an object in JavaScript. Objects in JavaScript that's not an object. An object is an instance of a class. That word just doesn't get used correctly in JavaScript.
What language is it called?
Python for one, but hash and dictionary are the same thing. A hash is the like computer sciencey term. So what a hash does is it gives you a way to handle random insertion and access in a like reasonably efficient way. So for example, I have something with cat, dog, and bird. And these have values on. So what we do is we allocate a bunch of space for this hash. And when I want to add cat, think about like that number substitution thing. Or this becomes 3, this becomes 1, this becomes 17 or whatever. So we add all of that up and we get whatever that would be, 20, 21. And so at 21, it's 3. And then this one ends up being 14. Well, 14 is 2. And so whether we're writing or whether we're reading, it's equally efficient, no matter how big this gets, to add something or read something randomly. It's pretty cool because we're dynamically calculating where something is, but we can recalculate that just as easily. Kind of neat. All right, so can anybody see the problem that we'll inevitably run into with that? No, that's fine. You give me the key, I'll give you the value. That's the deal we're making with the hash. What problem are we going to have? When's it going to break? What happens when I add tack? Hashes to the same value as cat. Uh-oh. So that's called a hash collision. How hashes handle that is they go, oh, okay. If they end up at the same location, then we're going to kind of put an asterisk on that. And then those hash based on something else. They almost like nest, kind of. That's how they work in every language that has them. The problem is that if I took up all of this space for my hash, ideally, every single thing that I add to it gets spaced out relatively evenly. It's making good use of the space. When things start hash colliding a lot, like let's say this ends up being a really popular hash, then I end up with that, and then these collide, and so then I gotta start going like that and like that. All of a sudden, not so fucking efficient anymore. And so different languages will implement the algorithm that generates this hash in different ways to try to make it as evenly distributed in general as possible. That's hashes. Talked about sets. Tree, think the DOM. So that's a tree. If there's only ever possibly 2 children for it, we call it a binary tree. And there's certain operations we can do on a binary tree that are really efficient. For example, if we're trying to do something like a maze, we can go left or right. Really easy to solve with binary trees. It's also really easy to sort things in binary trees. We go, okay, well this is less and this is more. And so we're trying to find the lowest value of something. Less, less, less. All right, well that's the lowest.
So it always reads left to right, lowest to highest.
That's a good question. So we could so that's called depth first. Breadth first would be, well, I go here, and then 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 here. So it goes breadth all the way down. Or we can go here, 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 here. That's depth first. Some operations are well suited for one, some are well suited for another. And then lastly, a graph is like a tree, except it can come back in on itself. And then we can do cool things with graphs like give them weights. This is 2, 1, 10, 5, 6, 2, 1. Find the cheapest route from here to here. And so then you calculate all the different ways you can get there and you add up their numbers and see which one's the least. Can anybody think of an example of where we would use something like that? Traffic, or the traveling salesman. Yeah, traveling salesman is like, what's the most efficient way for the traveling salesman to hit every house in the neighborhood? And like part of the challenge of it is that it's, I always forget, it's easy to get there, but it's difficult to verify or something like that. Traffic, that's how Google Maps works. Here's all the possible different ways we can get there. We weight each one. That might be based on distance, that might be based on current traffic, that might be a combination of those things. They each get a score. We go through all of them, find the one with the lowest score. That's your suggested route. Absolutely. Exactly. All right, those are all of the common data structures. The important thing that I want you to come out of this with is describing how they're used. You don't have all those memorized, it's going to take a sec, and you're going to have to practice with them and all that kind of shit. But tell me what questions you have about how data structures are used. Anything that you expect is going to change size often. Way more memory efficient to use a linked list for that. Also, randomly inserting something anywhere in the list, also way more efficient with a linked list than it is for an array. An array, we have to find the index, we have to split it into 2 arrays, we need to add this, we need to join all the arrays together. Versus this, you just move some pointers around. So a real world example, I am, let's see. When do we need a lot of random insertion, a lot of random, but not a lot of random reading? Sure, I'm trying to sort something. And as I'm sorting it, think about how you do it with cards. You're kind of putting the cards in random places. Linked list is a good like placeholder for something like that. Because I don't also need to like randomly get the 14th card that I'm holding. Linked list is a good solution for that.
I think one of the applications of the links is to store the same information because you don't want the other user to directly into the cloud. You have to go through multiple clouds to put the description on this cloud. Something like that. Like for example, you don't want that like inbound really have multiple departments, you have to go in the same way, you have to go through each department.
At a high level, absolutely. As a metaphor, I think that like linked list is one of the ones we probably use the least because to us in JavaScript and Ruby land and shit, just use an array. It has all of this shit in it. We can do all of these things and then let the compiler or whatever figure out if it actually needs to be an array or a linked list or a tuple or whatever. Some of these, as I mentioned earlier, stacks and queues, graphs, we actually get a lot of mileage out of using those as metaphors. Same thing with trees. Like the DOM is a great example of that. But like actual stacks and queues, we don't need them in high-level languages. Those just get handled by lower-level stuff. Other questions about describing how data structures get used? Mm-hmm.
When you make like requests and they add to the stack, or I guess I don't know if that's what you said,
Mm-hmm.
why is it a stack? Why wouldn't you want the first thing that goes into you? Why would you want it to execute in order?
Wonderful. Great questions. Call stack. So I say I'd like you to perform this operation. And the process of performing that operation, it goes, cool, well, I need you to do, to finish doing this, I actually need you to do this other action. And you start doing that one as like, part of this action is actually doing this one. And then what you really need to do is this one. So then you start working these off one at a time because you need to do all of these before this one's actually finished.
But some of those on top of it could be unrelated. Are they necessarily related to one another?
So in the example that I gave, they're all like sub-tasks of the first one you were trying to do.
Yeah.
So let's say we're also, and I think this is kind of what you're getting at, while this is working down, we click on something else and start just adding other shit on top of this. No, that's exactly the behavior, is that it adds it here. It doesn't enqueue it,
Yeah.
throws it on top. So we're doing the most recent stuff first there. The like honest answer of why it works that way is because they use a stack to model this problem. You could also say that, all right, the stack is only taking pushes once it's empty. And so you could design it such that, and this might be how it works, I don't know. We work all of this all the way down, and meanwhile we have this stuff that's getting enqueued over here. And once this is empty, we start pushing those into the call stack. So we have to explicitly declare how big this stack can get. Let's say it's 10,000. What happens when I push something on top? It's just like the bits are piling up on your computer. Ah! Other questions about how data structures are used? You can implement them in JavaScript, but keep in mind that you need some kind of like backing store where like we're actually keeping the data. And JavaScript probably going to be an object every single time. So, and then your JavaScript is a suggestion to your compiler of how to actually implement it. And then your compiler takes its recommendation of how it should actually be done and compiles that down to C++, which compiles down to something else, which compiles down to something else, which compiles down to something else. So you don't get like the performance benefits that are 80% of the point of this. However, as I mentioned, you do get some like metaphor benefits. And this gets to like the thing that Jesse was mentioning, where when we constrain some of these operations, then we get a lot more confidence that we can't do any illegal operation. And so you might implement a stack from scratch in JavaScript. Don't do that, but, well, I mean, you're gonna have to do that for the next objective, but if you implement that from scratch, like you get that safety, it's a lot like type safety, and that like, I know I can only perform a legal operation on it, but you don't get a performance benefit from it, really. It's my favorite kind.
Like, how does the compiling to like C++ work? Is it how fast is that process?
Fast as hell. It works, so I'm gonna punt on your question, but I'll give you a resource to dive into. Jit Compilation, just in time. When you write JavaScript, it's compiled to C++ in real time. And your browser actually does this magnificent dance where it like looks for common patterns and then in real time creates optimizations for those. And as your usage in the application changes, it redoes those optimizations and it's sending those down to C++ and it's using the little chunks there. It's a beautiful coordinated dance that it does. And the fact that it does it in real time is bonkers. Anybody know? The very same. Anybody, it's less than that. We did it in like 6, I think. Good old Brendan Eich. Brendan Eich was an engineer at Netscape. Mark Andreessen told him, hey, you got to make one of these little scripting things that'll help us win the browser wars, which was a thing in the 90s. Internet Explorer versus Netscape, and like you paid money for it was this crazy time. But yeah, that was like a project one week. Is can you make a little scripting language for me that we can run in our browser that Microsoft doesn't have? And he did it, and for a variety of like bizarro historical reasons, including like Microsoft had a competitor to JavaScript, it's called LiveScript, I think. And it was all these like, oh, we can't support theirs because then people will use their browser, so we'll have our proprietary lock-in in our browser, and then Flash was going to make all this irrelevant because you have your browser install a Flash plugin, and then you can write Flash and do all this cool interactive stuff. And all of that shit just kind of collapsed, and everybody consistently underestimated JavaScript, so it just flew under the radar. And as all of the like combatants lay dead on the battlefield, JavaScript was all that was left. And so now everybody uses JavaScript. It's wild. Brendan Eich went on to found an organization called Mozilla, which is still around to this very day. And this is the most important part. So Brendan Eich, Twitter. Let's see. I got this going on. Hey, it's one of my favorites. No, it's about the Mighty Mighty Bosstones. Cool. Back to the objectives. Describing how data structures are used. Questions?
Last one for me is on maps. When you guys
like maps and weak maps and that kind of stuff, yes, they are a data structure.
Gotcha, are they different from one of each other?
Yes. God, I'm spacing out a little bit. A map is like a hash, except it's something about how the address is calculated that's different. And I'm 90% sure it has to do with a much more limited range of operations. They calculate where the thing gets stored in such a way that if we don't have to support all of the exact same things that a hash does, then we can make something like sorting it way more quick.
Can you just go quickly over some research in sort
Not today.
nothing
So that gets into algorithms, which is the other half of this. As to say, all right, what ways can we sort an array? What ways can we sort a stack? And there's a variety of different algorithms for those. Or how do we find something in a linked list? And there's some like very counterintuitive but fast ways to do a lot of those things. Other questions about describing how data structures are used?
What is just maybe what's the best language to learn this from?
Best language to learn data structures in?
Because I feel like ChatGPT pretty good to have.
Mm-hmm. If I had to do this, Rust would probably be the first one to grab for. Rust is a lot like C++, but I mean, C++ is 40 plus years old at this point. Rust solves the same problem that C++ does, but accounts for a lot of the things that we learned from having 40 plus years of C++. That's kind of like the go-to super low-level language right now. Cool. Here's what I want you to do. Let's take 4 minutes, and I want you to write. Somebody asked you in a job interview. I'm not going to ask you anything about the data structures right now. Can you describe what they are, how they get used, that kind of thing? 4 minutes. Go. You too, Arlene. You can Slack it over to me.
Like individually?
No, just broadly. You can use examples. What are data structures? How are they used? Actual conversation I had with Schlesinger. In brighter news, I resisted the urge to make name withheld know what an entitled fucking baby he is. She said, "Good for you." I'm up for a Nobel Peace Prize for it, actually. right, slack it over to me. Outstanding answer, Arena. Good answer, Katie. I didn't mean to make that sound like it was worse than Arena's answer. It's also very good. I was gonna say good answer, Gage, but Gage just asked me a completely unrelated question and isn't in here right now. Cool, nice job all. Sounds like we get it and ready to move on. So I want us to implement a stack. So a stack has three things I want. I want to be able to get, let's see, I want to push something onto the stack. I want to pop something off of the stack. I want to peek that's looking at what's on top of the stack without actually taking it off, because pop removes it also. And I want to be able to get the length. The challenge that I'm laying out before you is I want you to implement a class that does all these things. So you should start with class stack. It should probably have something like data equals array. And then everything else is up to you. Let's take a couple minutes on this one. Oh, also, can't use for each or map or reduce. I can't imagine why you would in these, but we're trying to stay low level. That means ifs, for loops, real bare metal, no declarative programming kind of stuff. So let's take a couple minutes and see if we can get this figured out. Go! In JavaScript. You want it in Ruby, you could do that too, I guess. All right, you can keep working on it if you'd like. I'm going to work through a little bit myself. Feel free to abandon ship and follow along with me if you want. All right, so I make a stack.js file, nothing up this sleeve, nothing up this sleeve. And come on, man, languages. Okay, so I make the stack class. I make data equal to an empty array. And I need push, pop, peak, and length. So push, pop, peak, length. All right, I want to push something onto the stack. How do I adjust this to make that right? How about I take in an element? And now what? All right, we can type the whole thing. It's all right. And then might even return that too, because I should get the element back when I. Actually, no. I don't think push doesn't work that way. Pop. This I always want the thing that I'm popping off. I want to access that also. I could for peak.
Check for which stack is empty for the pop.
Oh, sure. I like that. And how can I do that? I haven't implemented it yet, but I could do this dot data dot length. I could also do this dot length. Because that's one of my things I want to implement, right? Cool. And the length of this is going to be this dot data dot length. Okay. And then if I want to peek, walk me through this. How do I take a look at the thing on top of the stack without taking it off? Mm-hmm.
How does pop know what the element is? Does it pass
Oh.
through again?
Nope, pop doesn't take in an argument. Good call. How do I write this?
So what is the purpose of peak?
I want to see what's on top of the stack without taking it off.
Oh, okay.
Can you access the last element of the array?
Mm-hmm. How do I do that?
Data, well, I guess you set it equal to a variable.
Don't have to.
Okay, data brackets -1. Is that it?
Not quite.
Okay.
All right, I have 5 elements in data. How would I hard code a response back to that? To peak?
You would return this dot data index 6.
Other way.
Yeah.
4.
Yeah, we can't have.
Okay, so if I know that I have 5 things in there, I would do that. But this is dynamic, so what do I swap 4 out for?
This dot data dot length minus 4.
Yep. Okay, so that gives me
What am I
that.
thinking of? Is that
You
for
can
like,
do -1 splice or something.
You can't do negative indexes in JavaScript, but you almost definitely can in Ruby.
Oh, that's what I did.
Okay. What if I have nothing in there? I end up with this dot data at -1. Yee. So what else do I need to do?
If condition, if statement, if that for any reason, that equals 0. Yep.
Cool. There's a stack. So if I do something like node, I think that's how we do it, interactive. No, that's not it. So if I do something like call stack equals new stack, and then I do call stack dot push an instruction, and I add another instruction, and I add yet another instruction, and then I do log call stack dot length, call stack dot peak, and call stack dot pop. What should come back in that console log? Add one more. Colin.
Read yet another instruction, two.
That's what I think. Oh, I'll bet this is some fucking spyware shit. Any day now. Good gravy, this is getting old. All right, so instead, I'm going to run it in my browser. Three, yet another instruction, yet another instruction. Two, nailed it. That's data structures. And if you want to see a whole bunch of them, including all the ones we talked about today, over my knowledge wiki, here's everything you need to know about lists, including what the class looks like, stacks. Hey, what do you know? Pretty close. We didn't have top. That's a top is the end of the stack. So that's like without using the actual array.length. If we had to do that by hand, we can keep track of what the last element is that way. Queues. Priority queue. That's where like something can jump ahead of something else if it's more important. Linked lists. Doubly linked lists. Circularly linked lists. Dictionaries. Oh, this says dictionaries and hashes is different. I think the difference is that dictionaries don't necessarily do that hashing to spread stuff out. Yep.
The conditional where you said if this dot length is greater than 0,
Mm-hmm.
why is it this dot length and not this dot?
because I was using my own implementation of this. For example, if I didn't want to use the built-in length for array, because remember, like, as somebody pointed out, this is all kind of made up in JavaScript. Like, we don't need any of this shit. But let's assume we had something where we didn't get arrays already as like a built-in thing, so we don't have a dot length that we get for free. One of the things that I had in there was like, all right, let's say we can't just keep track of the length automatically. So we do something like that, and then maybe we do something like top, or this dot top, and increment it. And then this becomes a lot more like this dot top plus 1, because we don't necessarily have access to one of those magical things underneath. Another way you could think of this is like, what if we didn't have an array here? What if this was a string where every time we want to separate elements, we do it with a semicolon or something like that, or a percent sign? It's just some characters. Because at some level, like down in the compiler, there is no array. All we have is just some fucking characters. And so we want to make up something like that. Like, how would you implement an array from scratch? Well, your data might look something more like and then if I want to get the number of items in this, I count up the number of percent signs. Or I want to get the second element. All right, well, I go until I get to a percent sign, and then I stop when I get to another percent sign and give you everything in between. And that's an array. At some point, this has to get implemented by somebody somewhere. So that's why I did it this way.
What is this dot length?
This.
Oh. Oh my god. I was literally in my mind thinking of the dot length that we took on the array, and not the function that we wrote. Never mind.
Questions? Thank you for this hopefully riveting introduction to data structures. All right, cheers.